Good morning. Let's wait a couple of minutes. Maybe the traffic today was unusually heavy. I was afraid I would be late. So I just want to make an announcement. I know that normally you wouldn't have any labs on Friday, but due to the holiday, it happens, and sometimes you may have conflicts with your work or something, so you can try to do it today. Or, as you know, I'm just listening, how do I sound? As you know, technically, you're allowed to drop one lab grade if you want to. I just would recommend to do this lab anyway, because it's supposed to help you with preparation to the exam. So one more minute. Some object, maybe a ball, something else. Big forces. Magnitude of each force. So, the magnitude of that force will be a number. Magnitude for the net force. Interesting. need to make a copy of the picture. What do we do? Because we need to add vectors, right? That result, from mathematical point of view, that what we call here network. This side shorter than 6. Diagram 30. Not 36. The force is always the result of interaction. Objects. So something is acting. Object. Force is a specific factor. Force of gravity. Force of fear. Force of friction. Surface. Here, the source of the force acting on the lady propelling her ahead. Well, every time when we needed to solve a problem about forces acting on an object, we needed to draw an object and forces. That's it. But that has a name, three-body diagram. Here, draw several three-body. The sentence means don't really actually draw an actual object, just draw a representation, like a dot or a box. The lady. Wall. Do we draw the wall? Well, we could have, but we don't need it. We need to draw object. Now we can start drawing forces acting on it. Force from the wall, that force propelled, has no special name. But we know from our everyday experience that water should exert some force. forces already shown to you. One guy which pushes, there's a frictional resistance. Technically, we should add two more forces. Everything what is happening on the Earth experiences force of gravity. But also it doesn't fall down through the ground because there's another force. That force we call normal force. Now, every time when we draw a diagram, try to indicate the strength of the force by the length of the arrow. And finally, set up. Well, not this particular one, as two objects connected. So we have two objects. We need to draw a three-body diagram for each. So, for example, number one, number. Now, how many forces are acting on the object number two? Normally, there is no touching between ball and there's a pulley. So gravity force due to the string attached to it, we call force of tension. Object number one, same string is attached to it, so there is also force of tension. But no force which prevents it from falling through the table, force of gravity, and in general, force of friction acting. Normally we would neglect force of friction. But we need to remember it does exist in general. Starting happening again. Things getting broken. This is a weight which can adjustable weight. The heavy weight is actually 1 kilogram, a string attached to it, right? So everything going to happen if I attach this weight? Nothing. Right. What is the force which prevents this from sliding, despite the fact that there is some force pulling in it? Friction, of course. How can we eliminate friction? Well, we can put some oil, or we can put this on wheels. But we also can, if you want to just make it move, we can add some extra weight and let it go. And you can see that it actually was traveling faster and faster. So there was some speeding up. If velocity changes, that means acceleration is not zero. That's a very important fact to remember. We will use it again soon. Now, these diagrams are bad. They're not wrong. Bad. What do you think? Yeah, they have no labels. So the force of gravity we usually write force of gravity or mg because we know it. Friction or resistance, R resistance. Normal force we use either Fm or just capital M. So number two. Well, these forces have no names. Let's apply forces. We call them 1 and 2. But this is again of tension, either F with the subscript or just a capital. If these forces have no name, each object for each diagram, we can calculate the net force by adding forces as we also as we know. Always use components. As long as we say this is a vector, that automatically means we can anything we've done before with vectors. Which is a good thing because now we know everything about vectors. Now we have two different situations. Very different. One we call equilibrium. And equilibrium satisfies these two conditions. Number one, net force, the sum of all forces, has to be equal to 0. That includes the case when there is no force at all acting on it. And second condition, the object is not moving. That's what we call resting. So if net force is 0, and of course, in general, some of its components has to be equal. Second situation when net force is not 0. We already saw an example. Results in acceleration, that object was sliding. Now, here at the top, experiment looks like this. I give it a push, and it stops. So that instant when I gave a push is not a part of the motion. Yeah? It's like before that. We start the stopwatch when it starts moving, not touching my fingers anymore. Starting from that moment, it was slowing down. Acceleration was opposite to velocity. And clearly, in this situation, when it was slowing down, we had three forces acting on it. That was force of gravity, but to eventually stop the object. Now, as we know, in general, friction is impossible to completely eliminate, but we can make it almost negligible. Fields of bearings. In this situation, with the push, it keeps traveling practically with constant velocity until something else starts happening, until another force starts acting on it. In this situation, net force is 0, but velocity is not, so it keeps moving. We don't call it equilibrium. Very important to remember. If we say this word, equilibrium, that means this. Velocity is 0 and remains for a certain period of time to be 0. But sometimes, yeah, it doesn't really matter. As long as net force is 0, again, all components must be cancel each other out. This experiment and many other experiments which have been done for hundreds of years before us demonstrate the fact that net force is supposed to be related to acceleration of this object. When net force is not 0, velocity changes, acceleration is not 0. Net force is 0, velocity constant, acceleration is 0. So these two situations describe two more Newton's laws. First of all, Newton's first law. Newton's first law says that in order to move with a constant velocity, an object doesn't require any forces acting on it. In outer space, you can throw a ball and it will be flying until it hits the star or something else. You don't need to apply force to keep an object moving with a velocity. Net force is zero, or no forces at all. It will be traveling at constant velocity or being at rest. That's the first law. But if you want to change velocity, we have to apply net force, which is not zero. And that's the second law. There are different experiments people have done to demonstrate the importance of force. The amount of force matters. It results in different situations. Broken. So, stronger force results in a higher acceleration. I move these parts. I move these parts of this stuff very quickly. Fast motion, high acceleration. Another example. Now with additional weight. Of course, in reality, you would need to attach a motion sensor to measure position and velocity as a function of time, extract information about acceleration. As we know, we can do that, just select the region, click quadratic fit, and what do we see? We see that mass affects acceleration. The force is the same here. I don't change the fan, right? But if I make an object heavier, it accelerates slower at a slower rate. So all those experiments eventually led to an equation which we call the Newton's second law. This in the middle of the slide. The acceleration of an object is directly proportional to the net force acting on it, and inversely proportional to the mass of that object. We used to think of the mass like the amount of matter, how much stuff did we put in it. But Newton said it's more than that. It's related to acceleration, which this object has when net forces start acting on it. The heavier the object is, the harder to change its velocity. That's what it is. Call it inertia, actually. And now we know basically everything starting from this. Theoretically, you're ready for the exam. That's it. Nothing new. Well, first we just need to practice like Newton's second law. Please take a minute and copy, draw the free body diagram again for both objects. First time you saw how I was doing it, but watching how someone does something is not learning. And also, now you should bring intuition of what you saw and add pre-shocking, a vector which represents vector which represents part where you should use your imagination. Very important part analysis because acceleration is related to force. Okay, we call it the object number one. Velocity was zero. What's the direction of velocity for the object number two? Direction of acceleration for the object number two. Now, exact No. All the acceleration direction. Let's say it's, you have to choose a direction. And we have a relationship between what's happening to velocity and acceleration, right? So we have to go back and remember that relationship. What's that relationship? Happening to velocity. Values. How do we relate directions? By times that. But this slide, I remember, that slide had 4 cars. And 4 pairs of arrows for velocity, acceleration, velocity. Right, so you don't get connection between velocity and acceleration. And it is speed up acceleration. Point down acceleration points up and down. Sometimes in your problems, by slowing down, and velocity, number 1 points totally, which means points horizontally. And now I want to make an important statement. Spring is not a spring. So every object they connected by unstretchable strings. Every object travels same distance over same time, so they always have magnitudes for velocity. One more time today, I will solve. Now, equilibrium. Please, anyone, answer this question. How can we select X and Y axis? Answer is anyhow. Sometimes we have to use this flexibility. Well, again, I know everything. That should have been several slides. But first, gentlemen and lady, I need your help. Before solving this problem, I want to show an example related to the lab. Here we have 3 scales of paper. All I want to ask you to do is just oops, okay. these strings. Grab it and pull this, grab it and pull this a little. So we can, yesterday we saw that we would use only two scales. They show exactly the same magnitudes. Yeah? Now, of course, magnitudes are different. We can read those magnitudes. This is 6 newtons. This is 10 newtons, and this is about 14 newtons. This force points that way, this force points this way, and this force points this way. And all we need, that's data. Now, how can we use this data? How can we use this data? We can prove that in equilibrium, and that was an equilibrium, again, if you look, there is a little knot right here. This object was under influence of those forces, and it wasn't moving at all. So, for this object, we can prove that the sum of all forces should be equal to 0. What would be the easiest way to do this? Well, you would use two axes like this, x and y. In this case, first arrow would have two components. Second arrow would have two components. And the third arrow would have two components. So you would have to use 6 components. The easiest way to make your life simpler is to choose one of the forces as one of the axes. Which one? Doesn't matter, of course. So, for example, instead of using this, you can use this. I can select this direction and call it, I don't know, y. As we know, the axis is a ruler, has no end, so it goes both ways. And now automatically the direction of the second axis is fixed because it has to be perpendicular to the first. So I just have to draw a perpendicular, call it x. So what do we see now is, well, 1, 2, 3. Of course we need this, measure angles. But if we measure angles, let's say this is theta 1, theta 2. Now we can write x and y components for each force. For example, F1y, Fyy, positive or negative? Negative, because it points opposite to axis. And again, what do we do? Vectors. So we have to be familiar. Negative should be negative. F1 times cosine of this angle. F1x, also negative. Negative F1 times sine of this angle. F2 components. X components should be positive. So F2 magnitude times sine, but the y component should be negative. So negative F2 times. Now what's good about this force? What number should I write for the x component? All right, should. Check, this is my triangle. Triangle I use, this is the angle I've introduced. I could have used a different angle, but I want to use this one. F2, F2y, is opposite, so I have to use. That's just a matter of actual labeling. I could call this y and not x, for example. You know? But every time when we use a triangle, we just have to use the triangle wherever it tells us. We just have to write it here. But here, what should I write now? X component of the third force? Zero, because it's perpendicular to this axis. It has no discal square. And this is just that force. That's it. So that's what makes this calculation easier. And of course now, if we measure accurately, calculate these numbers, and if we add those numbers, we must. If we don't get zeros, if we get huge numbers, so our measurements is wrong. But if we get numbers close to zero, that means, yes, we proved the fact that in equilibrium, net force is equal to zero. I'm going to leave this here, but now we can go further to solve an actual problem. This one. Problem. First, I want to ask you a question. You need to draw a three-body diagram. Body diagram has to show all forces acting on the subject. Show all those forces. You can count them. One force, you should cancel one. Forces, you should cancel. Forces, you should cancel. But if you see four forces, four. Number. Now, but these are almost even. So, how many forces did you choose? Count it here. Count it, we don't really mean. Gravity. No doubt. One is provided by the cable. And is provided by the wall. Now, the fourth force was suggested, the force acting from the lid on the wall. That force is acting on the wall. Force is acting on a different object. Should we use it for the three-body diagram of that? 5 times 10, 550 newtons. What else do we know in this triangle? Angles. Be careful with the which angle is which. This angle. Vertical direction and the tension. Where is my tension? 31. This part is not related to physics or even jazz. Now 15. This angle is 15. Degrees angle. So that's supposed to be again 31. That is the geometry. What we have now is two right triangles. Starting from now, all we have to do is just use equations for right triangles. Example, the side AC. From the top triangle, it's related to FL. From the bottom triangle, it's related to tension. From the top triangle, AC should be equal to hypotenuse FL times cosine over 15 degrees. But from the bottom triangle, the same AC should be equal to the hypotenuse, which is tension, times sine of 31. That's done. Okay, this is basically now the vertical part, the vertical part. Well, what I see is that plus CD give MG, the whole length of MG. BC, this is this side, plus CD. But related to L, say top triangle. Hypotenuse times sine of 15 plus CD, that side, is related to tension, tension T. Together we have 550. Tell me, equations do you see? How many unknowns? Starting from this, only similar to you've done before when you've been solving a problem about person walking west and east. And you also had two equations and two unknowns, and you had to fiddle with this mathematically to solve. So that means I can move on. But you will have solved practically exactly the same problem. Well, further investigation of the Newton's law This is a very simple example. Car, normal force, gravity is supposed to be equal to 2 pounds in kilograms or 2,000 kilograms times. We also see 2 forces directed to the right, 1 force directed to the left. Well, strictly speaking, this is a 2-dimensional situation, but not because the object is moving 2-dimensionally, because forces point in different. However, it is absolutely clear that they push it horizontally, velocity points to the right. And if there is any acceleration, right, they push it faster and faster. So which means acceleration K, which in general might have 2 components. Reality has only 1. What number should I write for the y component of acceleration? Perpendicular to the y-axis. Technically, this is just what we call acceleration. From the Newton's second law, that sum of all forces is equal to F. We know how to use vectors. Yeah? We just write fx1 plus fx2 plus fx3 equals n times ax, and x normal plus fxn. Sorry, y. Right? Now, this is supposed to be equal to 0, which automatically tells us that Fy normal minus 20,000 should be positive y direction, or the gravity has a negative component. So this equation doesn't tell anything about acceleration, but it tells us how we want, if we want to calculate the normal force. They cancel each other out. And of course, calculate the acceleration, we just need to do this. 5 plus 395 minus 560 should be mass times the acceleration we need to calculate. But the numbers, that's it. Problem seems simple, it is simple. Distracted shift. General for all problems related to Newton's all of them. Not yet.
I have a question on the how do you solve at the end?
Now, finally, let's finish solving this problem. So we already know that force is acting on the object number 2. Down to this object and up to this object. Subject to collecting frictions. That's it. Now, say again the statement about accelerations. We know that they have chapter same magnitude. But the string, not just unstretchable, also very light. Normal string is not a heavy cable, so it has no mass, it's massless. Because of that, string actually doesn't change the magnitude of a force. The force on both sides of the string has the same magnitude. Massless, the magnitude of this force. These equations come from properties of string. Now we're ready to solve it. So, different textbooks actually suggest different approaches in terms of choosing reference frame. Some say use the same reference frame to all objects. Some say each object you can use your own reference frame. So the object number one. Again, not all forces of gravity cancel each other out. They don't matter. The only force is responsible for acceleration is the force of tension. And so tension will be equal to mass of the first object times acceleration. Object number two. Now we see x direction doesn't matter. We'll only have vertical vectors. So technically, what should we write? Tension is positive, gravity is negative, and the acceleration also points down, so it should have a negative component. Now tension will be equal to kilograms times acceleration. So tension minus 1 times 10 velocity is 3 times massive. Divided by 3 is 1. I want to again just stress the importance of terminology. We cannot say that acceleration number 1 is equal to acceleration. Magnitude of the acceleration. For force of tension. For 1 points to the right, tension number 2 points up. Different vectors have the same magnitude. Well, and how do we solve it now? Mathematics. general idea how we solve two equations. The equations are more complicated. The idea is to isolate one unknown in both equations. Or there's another way, you can add equations. All right, question number 4. To show you an experiment. One object, second object. Neglect any frictionless, but this question doesn't matter. And I'm applying a force. That's it. My hand touches this left side of this box, pushes on it and makes it move. But the box pushes on the second box and makes that move. So that's what we see. If you want to solve a problem related to forces, we have to write Newton's second law. But to write Newton's second law, we have to choose the object for which we're writing that law. And here, how many different objects of your interest, which we call a system, how many choose? While I've been taking up a picture very quickly. Line, box number 1, box number 2. Time-saving technique. How many? Question number 4. Well, first of all, if we see two objects, definitely we can choose at least two systems. So one kind of, but each object we see, call a system. Basically, we just point our finger and say, I call it a system. Call this a system. Then point a finger at a different number. I call this a system. No one can stop me from doing that. But where else could I do it? Yes. No one said that I couldn't imagine that they just nailed it to each other or glued up to each other. It actually absolutely doesn't matter. I can say, this is my system. So we can call 3 systems. And now, how many Newton's laws can we write? 3. For each system of our choice, we can write a law. So we have to choose a system and write a law. This is one, the biggest one. What is the mass of this system? 5. Combined system, combined mass. The force acting on it. Generic applied force. We also have 2 forces vertical direction, but those forces cancel each other out, they do not matter. So the equation for this system is F, well, basically it's X component of the Newton's second law, because Y components don't matter, cancel each other out. So F and nothing else, no friction, should be mass and acceleration, or 15 should be 5 times acceleration. can choose the small box as a system. Force acting on it. Force. I can call it blue, because it's acting on the blue box. Do we have vertical forces? Of course we do. Sometimes. Again, those forces cancel each other out. Have any additional horizontal forces acting on the blue box? Well, if we have friction. Don't have friction. Do we touch it on the right? No. Do we see any strings or springs attached to it? No. What is a source for this force? Every force has a source. For this force, what is the source? What? Green box. The green box touches it, the green box pushes. So the source for this force is the green box. I don't draw it because it's not a part of this diagram. So no forces anymore. So I can write an equation now relative to the x-axis. This force should be equal to kilograms times acceleration. Now, a connection between this motion and this motion. It travels same distance over same time. It's equally fast. They change velocity equally. So what does it say about acceleration? Acceleration. That's supposed to be number 3. This force is 6 newtons. Why is it not 15? Because 15 newtons force is not applied to the blue box, it's applied to green box. My hand doesn't touch here. See? I cannot put it through. That's why it's not 15. Don't forget that. Well, of course, now we can write the Newton's law for the big box for the green one. Diagram. This force acting on the left face of the box. Do I know this force? Same force of 15 newtons. Now, do I have any more forces acting on the green box? In physics, touching means interacting. This box touches this box touches this box. That's it. So there is a force acting from the blue box on the green box. Acceleration of the green box is still to the right, and it's still. So relative to the x-axis, 15 minus force of green should be equal to 3 times 3. The 9. 15 minus 9 is. Turns out this force is 6 newtons. Doesn't surprise us. Not at all. The Newton's third law tells us that when two objects interact, forces they exert must have the same magnitude. The force from green on blue must have the same magnitude as the force from blue on green. We just have it proved. That's it. Any questions? Again, this is a typical strategy. All the work. Similar situations might happen in real life. What is the difference between the top picture and the bottom picture? Draw a diagram. small car pushes there is a force acting on my car. I don't draw vertical forces, they cancel each other out. And theoretically here we may have a force of friction or but there has to be a force acting from the track back on the car. Truck on the car. In order to be able to push the truck, wheels supposed to propel the whole car, so there has to be also a force, we call it applied force, or generated by the engine. These are forces, and of course it might be a force of resistance. These are forces, so if you want to draw a free body diagram, we should have here, it would have been only one force. But we also have a connection given by the Newton's third law. This must have the same magnitude. That analyze this problem. And there's another connection because they travel together. Important to keep in mind possible connection. Here, a truck tows a car. Force acting on a car, resistance. That's it. Totally. Body diagram for the car is just this. From truck on car. Normal gravity cancel. For the truck, has to be a force acting back. Might be some resistance. But what does make truck move? First, engine makes wheels rotating, and that propels body diagram should have possible force of resistance. However, the equations connecting still travel together, same acceleration, still Newton's third law, same magnitude. Sample of analysis. This is kind of physics actually is rooted in, need to understand what is acting on what. The rest is just, after that, thinking stops, just straightforward application of the equation, axis, etc., etc. Well, let's briefly, it's not a question to answer for you, just think how many systems could you choose now? Box, one system, medium box, second system, box, third system. Where else? Are we done? No. For example, we can combine these two together. Or we can combine these two together. What else? Together, all of them, all three together. That would be And normally, in a case like that, you should start from the biggest system and gradually go down to the smallest system and see how it works. Here we have one, again, no friction, so we have 15 newtons to the right, and we don't know how many newtons. But here we have some. Here we have some newtons, right? But nothing touches back. So tensions, well, of course, all accelerations are equal to each other. This is what we call the coupled motion. They coupled. And what about forces? Well, Newton's third law says magnitude of this force should be equal to the magnitude of this force. Action. Newton's third law says magnitude of this force should be equal to the magnitude of this force. Here. Right, 15 should be. Sometimes we can very quickly find some new equation, a new variable, and then use it. In this situation, nothing is moving. So, for equilibrium, the sum of all forces should be equal to 0. Here, what do we have? mg, which is 30 times 10, 300 newtons. Tension. Now, it's a number, and when we need to relate one number with another number, fractions. Tension might be less than 300, equal to 300, or more than 300. What do you think? What tension? Well, acceleration is 0. Technically, we needed to write the Newton's law, right? Relative to positive direction, tension is positive, gravity is negative, should be m times y component of acceleration. But if there is no acceleration at all, that should be 0. But as we said, all ropes or cables we use are ideal. So they don't stretch, and they don't change the magnitude of the tension. They only change the direction. Here, same 100 newtons act from rope on hands, right? It's a part of this diagram. But according to the Newton's third law, if this is the force acting from hand on rope. Acting from rope on hand. Both have to be equal to exactly the same number. Ask this question. Right, 300 newtons acting down to the rope on the right side of this pool. 4 newtons acting down. Have 600 newtons acting down to compensate. Newtons acting here to keep it at rest. Questions? All right, thank you. You're ready for the last part of the homework. You're ready for the lab. You're ready for the exam. Technically, we're going to do more examples tomorrow. And tomorrow, hopefully, we're going to start a new topic, which will not be a part of this exam, but we still have to go ahead. The actual section is from 11